Swayam Prabha. Digital India. Educated India.
Welcome all of you to fluid mechanics course. Today we are going to solve the problems on fluid statics. Before starting that, again I repeat that these are the three books we follow to solve fluid mechanics problems, but today I will focus on the fluid mechanics problems in GATE exam and engineering service exams. Looking that, today I will cover with a introductions to hydrostatic bench experiment, then some formulas, then we will solve 10 problems from GATE exam and engineering service exam. Now, let us look at the hydrostatic bench experiment setup which is there in IIT Guwahati. So, this type of experimental setups which is called this hydrostatic bench experiment setup, you can see the pressure gauge, you can see the pressure gauge, you can see these mercury manometers. So, these are mercury manometers are there, these are U-tube manometers are there, and you can have conduct different experiments using this pressure gauge as measurements, the manometer measurement and U-tube manometers. Not only that, there is the experiment setups to prove the Pascal's laws that the pressures in a horizontal surface remains the constant. That what you can see, there is a different shape of the containers are there. So, when you fill up the fluid diffuser at the rest, you will have the same horizontal plane will be developed irrespective of whatever the shape of the containers. That is the hydrostatic if they are connected. This is what we discuss more detail while teaching the hydrostatics, basic hydrostatics concepts, and we also derive the equations for that. Now, I just write the formulas, okay, and just to have repeat the things what we learnt it in a fluid basic properties and the fluid statics, that the Newton's laws of viscosities which establish the relationship between shear stress and the velocity gradient, and this is what mu stands for dynamics of viscosity. So, that way this is the relationships as we discuss, the relationship between shear stress and the velocity gradients. Similar way also we derived the capillarity height in terms of the diameter of the capillary tube, theta c stands for angle of contact, the sigma stands for the surface tensions. So, we establish the relationship between capillary height, the d stands for the diameters, theta is contact angles and sigma stands for surface tensor force. The surface tensor force when you equate with a pressure difference and the area where it is acting it, the force both the side the force equating what you have done it, the force the net force acting on this part is taking care of the force due to the surface tensions, that what is here. And as you know very basic things, when you consider z as a at the free surface levels is a 0, as the j it is increases in the downwards, the pressure will be rho g z. So, that what is indicates of a linear pressure distributions when fluid is at the rest. But if you consider that the at the atmospheric P equal to P atmospheric pressures, and at the height h what will be the pressures, which is very simple, is P atmospheric plus rho g h is the height of this, rho is a density, g is a acceleration due to the gravity. And next one, what we know it, how a floating body's stability we analysis is with respect to Bm and the Bg, the distance between the buoyancy to metacentric points, the buoyancy to the center of gravity. That is what will be show us that whether the body is of a floating body is a stable or unstable conditions. That what we will get it. So, let me repeat these things, that very simple things as we discuss the Newton laws of viscosity, which establish the relationship between shear stress and the velocity gradient. Similar way we derive the capillary height will be a functions of contact angles, surface tensions and the D stands for here the diameter of the capillary tube, or you can equate the force acting due to the pressure difference and the surface tensions forces, that what we equated, and very simple, what will be the pressure distribution in a fluid which is at the rest, the static fluid will be the weight of the fluid divided by the area, that is what will be the rho g j will come it, or simple way if I want to know it, the if it is a z is a total depth of the depth of a fluid, and rho g, rho is density, g is acceleration due to gravity, the weight will be the rho g z into the area, divide by the area I get the pressures, the weight per unit area, that what I get the pressures, simple way P equal to rho g j. But when you consider P equal to atmospheric, then we have considered this part. So, very simple way we can compute pressure distributions when fluid is a rest conditions. Let us start to solve the problems. These very easy problems, that there is a square gate of a dimensions of 1.5 meter into 1.5 meters. One of the vertical sides of a fully filled water tank has one side on the free surface. It is hinged on the lower horizontal sides. Here it is a hinged it, and is held in a positions by a force applied on the vertical, the central line at a depth of 0.75 meter below the free surface. So, this is 1.5 meters and 0.75 meters below means 0.75 meter from the bottoms, from the hinge, this is what 0.75 meters, total is 1.5 meters. So, what could be the magnitude of this force? What could be this force part? So, this is the force, you can easily solve these problems. The problem is that we need to know hydrostatic pressure distributions, then we can compute the force due to the hydrostatic distribution. Once I know what is the force is acting because the fluid is at the rest and where it acts the force, that the locations. If I know the force, the center of pressures or the force where is acting it, if I know that to the force magnitudes or the at the locations where the force acts, then I can take a movement at the hinge locations to compute what will be the force component. So, the problems wise it is a very easy problems to solve it, only we need to draw the pressure diagrams, compute the force due to these pressure diagrams, and we need to find out where this force acts, the center of pressures, where the force act. Then we try to take the movement at the hinge locations, as you know it, the sum of the moments should equal to 0 if in case of the hinge conditions, that the conditions we use it to compute the F value. That is a very simple things. Let us have F as we used to do the flow classifications. Here is the fluid is rest, need not to draw any control volumes, but if you want to draw a control volumes, to draw the pressure diagram for that, we can do it, but I am not highlighting this the control volume in this case. Now, the pressures at the water surface levels will be the atmospheric pressures, and we can consider this atmospheric pressure is close to the 0, okay, that as compared to the pressure distributions. The pressure distribution varies linearly with respect to the depth. That is what will be the pressure distributions. The rho g h is here 1.5 meters. The triangular pressure distributions diagrams will get it, and we need to compute what is the force because of these pressure diagrams. The average pressures multiplied into the area, that is what will be the net force due to the fluid at the rest. That what will come it average pressures into the area of the gate. That is what will be this is the force will be act due to the fluid at the rest, and that what will act it at 1/3 distance from the base. As you know it, in a triangular pressure distribution diagrams, the resultant force act at 1/3 distance from the bottoms or 2/3 distance from the free surface. So, 1/3 distance locations, that what will be acted the F fluid, F we know it what is the distance from this. So, we just take a moment about the hinge to compute what will be the F. The force into distance, that is what is moment we take it. So, finally, it comes out to be 11 kilonewtons. Now, let us be another gate questions we can solve it, where as it is a diagrams given here, there is a semicircles cylindrical gate is there and force F is acting here, and there is a hinge at this point. So, we need to compute it. If this is the free surface, this is the 2 meter depth of the water is there, what could be the force is required if the hinge at this point? This is what the questions. Now, if you look it, we can have a flow classifications here, because fluid is a rest, density is a constant, and we can consider is a homogeneous. And what we need to compute for this case, if you look it, this is a curved surface. So, because of that, there will be horizontal force acting on this, there will be horizontal force act on this, also the vertical force is going to act on that. So, there will be two force component will come it, one is a horizontal force, another is vertical force, and another F which is applied to here. So, we will try to find out what could be the force component to compute, so that this will not rotate it. So, we need to compute what is the F is acting on this. If there is a two force component, one is a horizontal force because of fluid at the rest, also will be the vertical force Fb will act on that. So, this force will take a moment about this hinge, and that moment, taking moment of these three force components will help us to compute what will be the F component. This is what the basic idea to solve these problems. Now, to compute horizontal forces, what is going to act it. So, it is very easy that the pressures what will get it, that what will be the force into vertical projections of the curved surface area. That is what we derived earlier. So, we can compute it, what will be the force will be act on this, as this surface the pressure distributions varies like this, we can find out the pressures at the centroid locations and multiply this area of the vertical projections area of the curved surface. That is what is commit, which will be the force acting on that, but that force will be act to 1/3 distance from these bottoms. That is that since it is a 2 meter height, you have a 2/3 meter distance from these B locations. This is what the horizontal force what is acting it. Similar way, if I need to compute the how much vertical force is acting on this, so you can find out if this is my free surface, this is the area, the shaded part, will give a vertical force component of Fb1, but Fb2 will be the, all the shaded part will be the Fb2 part. The subtracting this part, that what will be net force, what will be act vertically upward directions. As you know it, this Fb2 will be the higher than Fb1 as the more area of the liquid displaced by this curved surface. So, let me compute it. The vertical force on proportion of AC, that what with the weight of the liquid contained in the shaded area acting vertically downward through its CG, that is Fb1. Similar way, if you look at what is the force is acting on the BC surface part, that what with the weight of the liquid contained in the shaded part, okay, which is acting vertically upwards. That what will be the Fb1 value, and the net force will commit the difference between Fb2 Fb1, that is the net force will be acting it. So, we can find out the net force will be acted the shaded part of this part only. So, that means you just find out the cylindrical area, what is the dimension of cylindrical area, volume of the cylindrical area into the specific weight of the water. That is what the rho into G, that what will comes out to be 15.41 kilonewton, which is the vertical force, the net vertical force acting on this gate part. Now, if I take a moment at the hinge locations, we remember it, the force into the 1, that is what will be the from the hinge, this is a 1 meter distance, vertical force and its CG is 4r 3 pi distance from these hinge locations, and this horizontal force into its the distance from this hinge, that what will you get it. So, these are the sum of the moment about the hinge should equal to 0, that the concept we have used it. Then you will get it F into 1, that is what will value will come it, which becomes 0. The force becomes will be the 0 value. Now, let us come to the another questions number 3. The cross sections of object submerged into a fluid consists a square side of 2 meters and the triangle as shown in the figure. Object is hinged at the point P is 1 meter below the fluid free surface. If object is to be kept in this position as shown in the figure, the value of x should be, what is the x value, so that this will be at a same position, the equilibrium positions, these are the hinge locations. But what is the basic concept of this submerged object? If you look at that, there will be horizontal force will be act from these sides, also horizontal force will going to act from this side, but those will be cancelled out. The same amount of horizontal force will act from this side, also same amount will be horizontal force FH1, FH2. If I consider, both will be cancelled out. What will be the difference? There will be the vertical force will be act on this side, also this side, FB1, FB2, and there is a distance from these locations. So, if I know these two forces and their center of pressures or the line of actions of the vertical force and what is the distance from the hinge, taking the moment at the hinge, we can compute it, what will be the x distance, the triangle should be there, so that the moment will be the 0. That means, the positions will be the same position at the equilibrium positions will be there. Now, as the object is in a positions, that means the net moment about the P should be 0, that is the concept. Now, let us compute it, what will be the vertical force in the AB part. It is very simple, is the pressure distribution is uniform here, and we know rho g into A, will be the force component, that what will come it FB1 will be the 4 rho g. Similar way, the FB2 for this part we can compute it, the volume of water above the plate into the rho g, that is the volume of the water, and to the unit weight of the waters. That is what in terms of x we can write it what will be FB2. Now we are equating the sum of the moment at the origins, that will be FB1 into 1, FB2 into x by 3. This will be at x by 3 distance from this. The CG of this part at this point, which is a 1 by 3rd of the x distance. So, that way we can take a moment at the two locations, at the hinge locations, and when you equate this moment, we will get x value of this one. So, if you look at these problems, it is very easy problems, only you have to resolve the force components. The first you resolve to find out what is the horizontal force is acting it in different surface. If these two surfaces are cancelling out, then you look at the vertical force components and their line of actions. So, if you know the vertical force where is acting it and the vertical line of actions, take the moment about the hinge, then you will get the what will be the x value. That is the basic concept here. Now, let us come to a manometer problems. So, there is a inclined manometer shown in the figure below. Reservoir is large, that is the its surface may be assumed to be remain as a fixed elevations. A is connected to a gas pipeline. The deflections noted on the inclined gas tube. This is what the inclined gas tube is 100 millimeters. The theta, the angle of inclined manometers, theta equal to 30 degrees, and manometric fluid as oil with a specific gravity of 0.86. What is the pressure at A point, which is a GATE 2004 questions. So, that way let me is a fluid in static problems. So, density is constant, fluid can consider is homogeneous. Now, let us have the assumption is that considering this manometric leg what we have, that diameter should be more than 12 millimeters. So, that there is no capillarity effect. Because of the capillarity, there should not be the rise and fall of the manometric liquid for this case. So, this is what the assumptions for these problems. Now, what I am doing it to equate these pressures to compute what will be the pressures acting on this. So, if you look at that there is no pressure variations between the C to A. This is the gas part, assuming it that since the density of gas is very less. So, let us assume it there is not significant difference variations of the pressure at the P and C levels. If it is that case, the PC, the pressure at these locations, we can compute it as at this point the pressure is equal to the atmospheric pressures. So, will the PC is equal to be the height of this manometric liquid, the vertical height, that what will become it, the 100 millimeters into sin theta, that what will be so also vertical height, and the specific gravity. If I multiplied it, it is talking about in terms of millimeters. In terms of millimeters as equivalent of water, how much the pressures is acting on that. That is what is atmospheric pressures divided by the unit weight of the waters. So, that way is equivalent to water, we have done it. So, that way the gauge pressure, the pressure difference between the PC minus P atmospheric, which is the gauge pressure, will come out to be 43 mm of the water value. Now, let us go to the question number 5, which talking about the capillarity and the surface tensions. So, this is what the engineering service exam paper, where the two coaxial glass tubes forming a annular with a small gaps. Okay, there will be annular, but the gaps are small,
immersed in a clear waters. The inner and the outer diameters are small d and the capital D respectively. What is a capillary rise of water in this annular? If the sigma is a surface tension of the water in contact with air and the phi is the angle of contact between the water and the glass tubes. So, these are simple derivations to find out a relationship between capillary rise with the surface tensions and the angle of contact for annular with having inner and the outer diameters of smaller d and the capital D. There is a very easy concept that as we derived in the theory classes, that whenever you put it any small tubes, annular tubes in a liquid, what we get it that the outside you have P equal to atmospheres, here also you will have the P equal to be the P atmosphere, because when fluid is at the rest, any horizontal plane, if you take it, the pressure should be equal. So, that is what this is the horizontal reference plane. The fluid outside, since it at the atmospheric pressures, the fluid which is inside in this capillary tube also will be the atmospheric pressures. So, P will be the atmospheric pressures. If that is the conditions, here also P equal to P atmospheric pressures. That means, the weight of this liquid which is capillarized from the surface, that what will be balanced by the surface tension force, as we derived in the theory class. This very basic concept. The fluid is due to the additions of water wall, that is what is upwards making angle of phi degree. Now, I have just equating this, since is the equilibrium conditions in the, so upward force is equal to the downward force. The upward force is a surface tensor force part, that what will act for a two different diameters, that what will be the different T1, T2, and this phi stands for the contact angles, that what will give us this component as the upward force. So, we can compute the downward force, which is the weight of the fluid, that what be confined by this the capillary rise, that what will be the phi by 4 d square by minus small d squares into h into the unit weight of the waters, that what will give us the weight, which is the weight of the fluid acting downwards, the upward part. So, if I just rearrange these terms, so finally I will get these ones. That is what very basic way I will get it, the relations between the capillary height, angle of contact, and these two are the diameter of annular systems, where you will have a, and sigma stands for surface tensions. These are simple derivations what we have done it. Now, let us, before coming to another 5 questions to solve, this is what the photographs, what you can see it. I attended this MOO ceremonies held at Kyoto University in Japan. What I want to say that if I try to understand it, how, what the success story behind a Japanese research to develop after the World War II, I can visualize they have the 3 human characteristics that what helped them to improve their economic conditions when after the World War II. One is no doubt is hard work, truthfulness, and the punctuality. But another things what I am to tell you that we always not have a habit to maintain a diary, but any of Japanese, if you look it, they are very good in maintaining a diary. That's the reasons they are keep it their brain is free. So, they are very particular to maintain a diary, the planning the activities very systematic ways. So, always if you look at Japanese, he always maintain a diaries to noting it, the calendars, work plan, job activities, all they noted on this, and they carry the diary wherever locations they go it. So that what is another characteristics what I observed it while I interacting with Japanese groups with whom I have been working on rainfall data analysis in northeast regions. So what I meant to say that in a fluid mechanics or any of the subjects, we always try to remember the formulas. Please don't remember the formulas, you try to maintain a diary for that. So slowly you can understand those equations and try to apply the formulas in the right place. So as a overall the design of the course, if you look at that, always I encourage all of you to derive the simple equations instead of remembering this total formula. That should be the idea when you solve the fluid mechanics problems. Let us solve another 5 questions on fluid at the rest conditions. The question number 6, that is what 2 pipelines, one carrying oil. The mass density of the oil is 900 kg per meter cube. Other one is water. It is connected to a manometer as shown in the figures. By what amount of pressure in the water pipe should be increased so that the mercury levels in the both limbs of the manometers becomes equal. The mass density of mercury is given here, which is 13,550 kg per meter cube. G is the acceleration due to the gravities. Now let me sketch it. So initial conditions what you have oil, you have the water, it is connected to the manometers, mercury manometers, which is having a 20 centimeter rise along this horizontal plane. This is the 3 meters, this is what 1.5 meters. As we increase the pressures, the mercury manometers limbs will be the horizontals. That means there will be this 20 centimeter, if you can understand, it will be make it 10 centimeter in this side and also the 10 centimeter from this side, then it will come to a horizontal plane. So it will be 1.6 meters, this side will be the 2.9 meters. There will be rise, there is fall. That what will be happen it to, in this case will be rise it, this case will be fall it, the total mercury will come it, these orientations will come when pressure in the tube is increased. So what we are going to do it, for these conditions we try to find it how the pressure difference is there over this plane of A dash and the AB dash. From that we can know it what is the additional pressure is applied here to make it the surface horizontal. So the very basic concept here just to try to understand it. So pressure is applied at a point, so pressure increases uniformly at each point of the fluid. So that is what the Pascal's law is. That is what the Pascal's law. Now we are applying for the first case, as I said it, to remain at the perfect levels, the x will be decreased from the left limb obviously, and there will be the right limbs will be the increase by the x value. So x will be come out to be 0.1 meters. Now I am equating the pressures P dash for this case. So I have the pressure at this point on this horizontal surface in these manometers. I want to compute what will be the pressure difference between this. Let B consider pressure at this point is P oil, at this point is P water. So P oil, then the specific gravity into the height. Similar way we can multiply it for water case as well as the mercury case. So if we rearrange it, the pressure difference between the oil and the waters divide by the unit weight of the waters, you will get these values. We will get this value which is equal to 1.51 meter. Now, the second case what we will consider when it is the mercury levels at the same level, okay, after increasing the pressure at this point. So, that what will be equal to Pa plus is equal to Pb, that will be the oil plus 2.9 into the specific gravity, and there is a pressure water and there is increasing pressure of Pb, that what will be divided by this is equal to this part. So, just rearranging this part, we will have a this component plus this component, and since this component is known to us, you can compute the Pb value will be 24.7 kilopascals. So, basically try to understand it. There is a two conditions we have, the initial conditions where the manometric liquids are in different levels, and then is the final conditions when we apply the additional force at this point. So, only we have applied very basic equations that in a horizontal surface, whenever you take it, the pressure on that horizontal surface is the same or equal pressure will act on the horizontal surface when fluid is at the rest. That the conditions what we have applied it to compute what will be the additional force is acting at the water to make it the mercury level is perfectly horizontal. Now, take it the question number 7. There is a ship of metacentric height of 0.3 meters. Its a period of rolling is 20 seconds. The relevant radius of gyrations is nearly, or what is the value of relevant radius of gyrations, that what is engineering service question in 2015. So, as you know that there is a metacentric axis, it has known the metacentric height, and it is also know it what is the time periods of ruling this ship part. This is just sketch to say it, the weight, the metacentric height and all the things. So, the ship rotates about its longitudinal metacentric axis, and it is considered as a pendulum. Okay, as a pendulum, it has a center of rotations at the metacenters. So, at the metacentric levels, this is what is having the simple pendulum oscillations happening it. So, if it is that, let me draw the free body diagrams. That means, if it is the metacentric height here, this is the object is moving like this, okay. The oscillating is like a pendulums. If that, we have a restorative momentum is moment of inertia into accelerations is will be act is what is the force torque momentum is working it, that is what unit weight sin theta into gm, and that what if we rearrange it in terms of angular accelerations of oscillating component, we will get this part, and as a harmonic components part if you look it, and finally we will get it the omega in terms of unit weight, gm, and I is moment of inertia. So, the return periods or the time periods will be the 2 pi radian by angular velocities, that is what is known from this part, and from this if r stand for radius of gyrations, we will compute it the capital T value in terms of r squares. We know the gm value, substitute it, then I will get it the r will be the 9.45 meters. Okay. R will be the 9.45 meters. Look at these problems. This problem is considered is a just like the ship is as equivalent to a pendulum, it is accelerating it at the metacentric height locations, and if it is a making angle theta, then what are the restoring momentum moment and what is the moment due to these oscillations. That what we are equating it to find out what will be the R value. What will be the R value. Now, take it the question number 8, which is a 3 fluid system connected to a vacuum pump, okay, where there is no pressures on this. So, that is what the vacuum pump. Specific gravity values are given in these figures, okay, that is S1 is 0.88, 0.95 and the water which is specific gravity equal to 1. Then if it is a gauge pressure value at P1, what will be the pressure at the P1 value if you consider the unit weight of the waters 9.81 kilonewton per meter cube. This is a very simple problems, that if I take a horizontal surface here, here the pressure is atmospheres, I can compute the pressure at this point also will be the atmospheric pressure. So, I know this pressure at this point is atmospheric pressure, I just equate it. If I compute the pressures from these vertical directions, what is the pressure is coming, that should be equal to the atmospheric pressure. That what is done it here. P1 is pressure at this point. As we go down the unit weight specific gravity into the height, the pressures of this fluid 1, then this fluid 2, the unit weight, the specific gravity H2 into H2 should equal to the atmospheric pressure, should equal to the atmospheric pressure. Just equating that, we will get the gauge pressures will be the negative of 8.79 kilonewton per meter square. So, this is very easy problems, only you have to find out where you have to equate the pressures, where you have to take the horizontal lines. So, that way you can equate the problems and solve the problems. If you do not take properly the horizontal surface to equate the pressures at 2 locations, then you try to do the mistakes. That is what I have to tell it. Another these are very interesting problems is that a droplet of radius r split into n small droplets. Okay. So, bigger droplets is split it into n number of small droplet of equal size. Find the work required given that the surface tensions is equal to the sigma value. So, that means that the bigger radius r is there and which is split it to the n small number droplets, and that is what is happened to go for more surface areas. As it go for the more surface areas, it is need to do the work against that surface area, increase of the surface area, there is more surface tension force will be act as we increase the surface area. So, that is what we are trying to look at. If a bigger droplet of radius r split into n number of smaller droplets, then how much of extra area, surface area we are generating it, and because of the extra surface area, how much force is required to give it to split into the n number of droplets. That the concept here, and most of the concept what will be considered as equivalent to a spherical balls, and surface is minimum, that what is surface energy is minimum concept what is considered, that is what is a stable consider for the any droplet. The first is that let us, since the bigger droplet is divided into n number of smaller droplet, the volume should be equal, okay, of the spherical volumes what you are getting it, that should be equal it. That is what for the, if it is small r is for the smaller droplet and bigger r represent the radius of the bigger droplet, that then we will get it the volume, and this side n is multiplied to find out for the n number of droplet conditions. So, we will establish the relationship of r with capital R and n number of things. Now, we want to find it increase in the surface area. Okay. We know for each spherical ball what is the surface area, okay, 4 pi r square. So, smaller balls will have this much of surface area and the bigger volumes. There is an increase in the surface area, that what will compute it. The increase in the surface area into the surface tensions, that what will give is the work done for that. That is what we have computed to compute the work done part. That just we need to compute increase in the surface area, and after knowing this increasing of surface area into the surface tension force will give us the work done part. So, the basically these problems does not have a much concept wise, only to equate the volume of droplets and n number of small droplet volumes, then find out what is the increase of surface area. As we know that this much of work need to be done it to split the bigger droplet to the smaller n number of smaller droplet, because this much of additional surface force is acting. So, that way force surface tension into the area will give us the work done component. Now, let me come to very simple problems, which this is the last questions what we are going to discuss is that there is a cylinders of 0.1 meter diameters, 0.375 meters high containing the water. It is rotated about the vertical axis at the speed of 320 rpm rotations per minute, so that a portion of water spills wet. Okay. So, if you consider a cylinder like this and you start rotating with a uniform speed of 320 rotation per minute, as you know it will create the free surface profile like this. So, the water will be spill it. As the water spill it, if it's make it the cylinder is brought to the rest, what could be the depth of the water in it. So, this is just a force vortex problems. Already we have derived what could be the force vortex flow distributions part. We are just using this formula to solve this problem. Now, the first what is that if n is rotations per minute and you compute the radius, then you can compute the angular velocity, it is 2 pi n by 60. That what will give us the angular velocity in terms of radian per seconds. As we are discussing it, that if this is the cylindrical object which will rotate with omega angular velocity, you will have the free surface profiles like this. The height h will have a relations with the angular velocity and the radius. That is what we derived in a forced vortex case. That what will comes out to be 0.322 meters. As you know it, volume of paraboloid is half of enclosing cylinders. So, we know the volume that part. That means, this much of volume vessels when full water conditions, and this is the volume will be spill out, the remaining water will be this much of volume. So, divide by this surface area we will get the depth what will be the remaining. Again, I am to just conceptually talk about this. When we are rotating a cylinders which is filled with the waters, as we have rotated with angular velocity of omega, then what will happen it will create a free surface like this of height h. The remaining amount of this is the amount of the water will be spilled out from this surface. So, as we know this, what will be the h surface will be generated, and we also know how much of volume water will be spilled out from this original amount of water we know it, remaining amount of the volume of water we know. From there we can compute what will be the depth, which is volume divided by the surface area, that what will be condition. So, with this let me conclude these lectures by solving these 10 problems. Thank you lot.